Okay, now let's see what is a connected and disconnected graph. So a connected graph is kind of a graph in which from any single node, if you start from any node, okay, so a graph in which one node, if you pick any one node and it will allow you to visit all the nodes, then it is called the connected graph. Okay, so if we write the definition for the connected graph, so it will be one node you can visit any other node, any other node. It's not like from one node you can visit all the nodes directly, but indirectly you should be able to visit all the nodes, right? Now, if we talk about the disconnected, now if we talk about disconnected, so disconnected is in which at least one node is not reachable. Okay, at least one node is not reachable. Let me explain you with example. Okay, so consider a graph is given like this: 1, 2, 3, 4. So in which if you start from any node, like if you start from 1, right? So you can be able to reach to all the nodes, right? 1, 2, 3, 4. So this is called a connected graph, okay? Where from any node, at least from one node, you should be able to visit all the nodes. So this is called the connected graph, right? Now, what is the disconnected graph? So disconnected graph is like in which there must be at least one node which you cannot visit from other. So 1 and 2, this could be a graph, right? And 4 and 5, this could be a graph. So these are disconnected, right? So there is no connection between, but this is a graph also, right? So this is also a graph, just to understand. Here we discuss, right? So what is a graph? It's a non-linear sequence, but here tree should be only connected with each other. But in case of a disconnected graph, or in case of a graph, I would say it is not mandatory that they should be connected by each other, right? So this is called disconnected graph. Okay, so this is one example, or if you can say this is 1 and 3, right? And there is a node called 4. So if you start with 1, we will be able to reach 3, right? And if start with 3, we will be able to reach 1, but we will not be able to reach 4. And if we start with 4, we will be able to reach only 4. We will not be able to reach to this graph, right? So this is called disconnected. But here, if you start with any of the node, you will be able to visit each and every node in the graph. So this is called the connected graph. Very simple. Difference between the connected and disconnected graph. Simple. Any doubt in this? No. Okay. Thanks, Rajat. Okay. So moving on. So graph is very simple actually. The only thing that you have to do is just do the traversals. Okay. Just do the traversals, build a basic understanding, right? And then it's very easy. At least the question asked in the interviews, right? In most of the interviews will be easy for you then. Okay. Okay. Graph, types of graph, undirected graph and directed graph, connected and disconnected, I will discuss, right? Now, there is a type of a graph called complete graph. Okay. Complete graph. So what is a complete graph? See here. So in which from each node there is an edge to other node, right? So here if you see from 1, if you want to reach 4, you will go to 2, then you will go to 4, or you will go to 3, then you will go to 4, right? But if from any node you can visit to other node directly, okay, from any node, you can visit to other node directly like this. So I will just redraw the last one. Okay. So it was 1, 2, 4, and 3. So this was the graph given in the last example we took in the last example. Okay. 1, 2, 3, and 4. Okay. Now to reach 4, you have to go via 2, right? So just connect it and connect this, right? So this graph. So here from each node, you can visit to each and every node, right? So there is an edge. How you will go from one to other? Because there is an edge between them, right? So it means that if there is an edge between each of the nodes, then it is called the complete graph. Okay. So what is the definition of complete graph? Each node have edges with all other nodes. Clear? Each node have edges with all other nodes, so it is called complete graph. Where, so if we say here that v number of vertices are there, right? So 1, 2, 3, 4, right? So how many number of edges will be there, right? How many number of edges will be there, right? So consider this one, right? So there are 4 nodes, right? So it will connect with 3 others, right? So this will connect with 3 others, which is v minus 1, right? So this will connect with v minus 1 nodes, but this will be followed for how many vertices? V vertices. So total number of edges that comes here is v into v minus 1. Okay. So what is a complete graph? Each node have the edges with other nodes. This is called the complete graph. Simple, right? Now, let's come to the next one, which is called cyclic graph. So cyclic graph is basically the graph in which the cycle exists. Simple. In the last example also. So it's like 1, 2, and 3. It's very simple example I'm taking. It's 1, 2, 3, right? So this is called the cyclic graph in which cycle exists. So called it cyclic graph. Okay. Now the next one is called weighted graph. Weighted graph is nothing more than that. Here in this example, if you see, right, in this example, if you see 1, 2, 3. Here we are saying that there is an edge between 1 and 2. There is edge between 2 and 3. There is a edge between 1 and 3. But if we say, the cost to go from 1 to 2 edges is 12. The cost from 2 to 3 is 2, and the cost from 1 to 3 is 10, right? So if we weight these edges, right, and some suitable weight we allot to these edges, right? So this is called the weighted graph. This is useful. Consider you want to travel from A to B distance, right? And it's given like distance of the multiple paths, right? So you want to travel from this to this, and there will be multiple paths possible, right? So what they will do, they will calculate the minimum weightage path, right? Minimum weightage path, so you can reach earlier, right? So the time is given, weightage can be the time here in these edges, right? So the time taken, right? So basically that is the concept when weighted graph will be used. Okay? Simple. Any doubt in this till now, and the types of graph from anyone? No doubts. Okay. Okay. Now let's see like what is the uses of graph, right? So where we will use this graph. Okay. Okay. Uses of the graph, right? So whenever we see the GPS, right, the GPS you use, right, to control traffic, to understand the traffic, to calculate the fastest route, right? So all these things are built by the graph only. Fastest route. Okay, so simply what it have the graph, right, and the vertices and the edges between them are weighted, right? You want to reach from A to B, right? And there are multiple hops considered between C, D, E. Okay, now from here you can go to C and then C to B, or you can go to A to D and then D to E and then this, right? So there is a weightage. Here it will take 12 minutes, here it will take 8 minutes, here it will take 2 minutes, here it will take 4 minutes, here it will take 6 minutes, right? So overall this path is better. Overall this path takes 12 minutes, here overall this path takes 20 minutes, right? So you will follow this path. How they will calculate? On the basis of weight, they keep on calculating, they keep on adding the best path, possible paths that we have now, okay? This one is the GPS one. Or any social media you use, right? Any social media you use, right? So like recently Twitter also using the graph database also. Not recently, it's long time back. So Twitter also, right? Or any social media you say like Facebook, right? So how Facebook do? Facebook knows that okay, A is the friend of someone, right? And A follows B, right? And B follows C. So whenever you're scrolling down, right? So you got some suggestions, right? You may also follow C, right? Why you may follow C? So they will show you the reason that B is a mutual contact. B is a mutual contact, right? So this type of a thing. And there is a one service that I am also working on, which is building relations or connections, right? So I started working on this service recently in my trip, right? So this service will use to do, so this will basically manage your connections. This will manage your connections similar to like this, right? So where A having some connection, right, and then you visit C's profile, okay? So there is a profile concept, right? And from A you visit to C's profile. So there, what is the reason that you will follow C, right? So how I will persuade you to follow C, right? So there we need some common connect, okay? Some common connect which forces you, which pushes you to follow C, right? So I will just check all the persons, right, to which A follows and those person follows C, right? So I would just want to know that, okay? Then I can suggest that okay, B is a mutual for both of you, so you can follow each other like this way. You can build the relation like this. So this is kind of a these are the persuasions that we derive. Okay, so simply if we do these operations, simple database. If we talk about database, now simple database we can use. But once it's come to a complex problem where 2 degree, 3 degree relations are needed, right? 1 degree is like this relation A to C. 2 degrees like 1 degree. This is 1 degree and this is 2 degree, right? So this is 2 degree relation and this is called 3 degree relation from here, right? So basically number of edges, how many number of edges are coming in between, right? So these are kind of a simple uses for the graph that we have in the real life. Okay. Okay. Moving on to the next set of thing, which is actually the starting of the graph problems. Okay, is representation of a graph. Okay, how we represent the graph. Okay, so in the last couple of slides, I have already discussed, right, how to represent a graph. But let's see. Okay, so there are the two ways to represent a graph simply. Okay, one is called adjacency list, and that is called the adjacency matrix. Okay, the second is called adjacency matrix. Okay, now a simple graph is given to you. It's like 0 is connected to 1, it's connected to 2. Okay, a simple graph is given to you like this, right? Now, adjacency list or the adjacency matrix. Let's start with the adjacency matrix here. Okay, so it's kind of a 2D matrix to store the relations, right? To store the connections. Okay, in which we have a rows and column which denote the vertices. Okay, and each entry represents whether there is an edge or not. Okay, so let's try to draw. Okay, so 0, 1, 2, 3. Similarly, 0, 1, 2, 3. Yeah, so this is zeroth vertices 0, 1, 2, 3, 0, 1, 2, 3. Right? So now let's try to draw the adjacency matrix for it. So for 0, is there a connection with itself? No. So add 0 here. For 0 to 1, there is a connection? Yes. Add 1 here. For 0 to 2, there is a connection? Yes. Add 1 here. And for 0 to 3, there is a connection direct? No. No. Now, whatever you are adding to 0 to 1, right? Same will be added to 1 to 0 because this is an undirected graph. This is an indirect graph. So if you added 0 to 0, 0 will be same. 0 to 1, whatever you added, you should add to 1 to 0 also. 0 to 2, whatever you added, you have to add 2 to 0. Okay. 0 to 2. So add to 2 to 0. And whatever you added 0 to 3, it will be 3 to 0. Simple. This is the what we feel, right? Now, for 1 and 1, is 1 and 1 connected? No. 1 and 2 connected? Yes. 1 and 3 connected? No. Simple, right? Similarly, what you have done will be replaced here 1 and 2. 1 comma 2 should be replaced with 2 comma 1. So 2 comma 1 will be 1 here. Okay. 1 comma 2 is 2 comma 1. Simple. And here we have 2 comma 2. So do we have a connection between 2 and 2? No. 0. Do we have a connection between 2 and 3? Yes. Simple. 3 and 1. 3 and 1, no connection. And 3 and 2, yes. And 3 and 3, no. So this is kind of adjacency matrix that we built. Okay, so we can track within which vertices have the relations, have the connections between them, right? So this is called adjacency matrix that we built. Now for v vertices or m vertices, to build this matrix, right? So to build this matrix, we need m cross m, adjacency n cross m, adjacency matrix. Okay. So to create the adjacency matrix with m vertices, we need n cross n, m cross m, whatever is matrix, right? Now let's move on to the next one, that is called adjacency list. So beside marking these 0, 0, 0, 0, right? So what we can do, we can simply say, right, okay, for 0, we have a connect with 1 and 2. For 1, we have a connect with 0 and 2. For 2, we have a connect with 0, 1 and 3. For 3, we have a connect with 2 only. Why to keep these things, right? So why to keep these things? So simply we will do here. For 0, we will say we have a relation between 1 and 2. For 1, we have a relation between 0 and 2. For 2, we have a relation between 0, 1 and 3. For 3, we don't have a relation with 0. We don't have a relation with 1. We have a relation with 2 only, right? So this is kind of a adjacency list we have. Okay, so this is kind of a adjacency list we have, and this kind of adjacency matrix we have. These are the two representation of graph. So any doubt in this? Because this is something which you need to understand to solve any problem in the graph section. No from Aniket, no from Rajat. Okay. Okay. Now, who wanna help me with this adjacency matrix to draw the adjacency matrix or the list? I would say list only, adjacency list only. So yeah. Anyone who understand the concept and want to help me out, or actually who don't understand and want to help me out. Subra.
Yes, sir.
So want to tell like the adjacency list for this?
So like we need to draw the rows and columns. Like first we need to draw the square, sir. Square
No,
rectangle.
this list I was saying.
Yes, sir. Like the matrix for the rest, right?
Ha.
Yeah, 0, 1, 3, 4, 5. Okay. From 0, it's like it's going to 1 and 3, sir.
0, it's going to 1 and
1 and 3.
1 and 3.
From 1, it's going to 0 and 3. 0, 3, and 5.
0, 3, and 5.
From sir, 2 is not this. Is
It's okay.
like should we keep 2? Okay, from 3 is actually going to 0, 1, and 4.
0, 1, and 4.
From 4, it's going to 3 and 5.
3 and 5.
3 can go 5 also.
3 can go to
5.
other.
Okay, indirect also. Oh yeah. Okay, 5, from 5 it can go to 1, 1, 3, and 4, sir.
1, 3, and 4. Correct. So this is kind of a adjacency list we have drawn. Okay. Now let's try to draw the adjacency matrix. So anyone else who except Subra who want to help me out with the adjacency matrix? Okay. Subra, can you tell for the adjacency matrix also?
Yes, sir. Like we need to like first draw the rows and columns like around this square.
Correct. What are the
0, 1, 3, 4, 5.
0, 1, 3, 4, 5? Zero, 1, 3, 4, 5. Yeah.
From 0 to 0, there is no edge, so it's 0.
0,
0 to 1, 1.
1,
0 to 3, 1.
1,
0 to 4, 0.
0,
0 to 5, 0. So
0. Okay.
from 1 to 0, 1.
So there is no need to check all of these. Like whatever you have done filled here, it will be same here.
Yes.
Okay. Now for this 1 to
So
1,
1 to 1 is 0. 1 to 3 is 1.
1 to 3 is 1.
1 to 4 is 0. 1 to 5 is 1.
Right, 1 to 5, there is a H. Okay. 3 to
3 to 1 is 1.
3 to 1 is 1, can be checked from here because it's an undirected graph. So this is 1 here. Okay. And
3
then
to 3 is 0.
2, 3, 0, 3, 2, 4, 1, and 3 to 5 is again 1. Similarly, for 4 to 1, there is no H, so fill with 0.
0. 4 to 3 is 1. 4 to 4 is 0, and 4 to 5 is 1.
Correct. For 5 to 1?
5 to 1 is 1. 5 to 2, 5 to 2, 5 to 3 is 1. 5 to 4 is 1. 5 to 5 is 0.
Correct. So this is the adjacency matrix we have drawn. This is the adjacency list we have drawn for the simple graph, right? So now if you think about, like, we have drawn all of this, right? So if you think about the traversal, right? So here you know which is to go. Here you know for 0 you have to go to 1 and 3. Here you have some zeros also in between. So there is a possibility that there will be a lot of zeros. It's called the sparse matrix, right? So there is a possibility there are multiple zeros, right? So if there are multiple zeros, there is no point of keeping those, right? So there is no point of using adjacency matrix in that case, right? The adjacency list will be suffice in that case, right? So some cases, in most of the cases, you will see that adjacency list we will be using, and adjacency list is also better because it don't have the sparse matrix kind of arrangement, right? If it is a connection, then it will store, Otherwise it will not store. Here doesn't matter whether it is a connection or not, it have to store all of those values, whether 0, 1 and of all the three, right? So this is called adjacency matrix and list. Okay, moving on to the traversals of a graph. Okay, traversal of a graph. So simply a graph is given to you, okay, and someone asks you to traverse. Okay, so there is a two ways to traverse a graph. Okay, so there is a two ways to traverse a graph. So simply what two ways we have in a tree, right? So we have a breadth first search, we have a depth first search, right? In the tree, right? But the issue here is we will basically follow the same process for the BFS and DFS that we used to do in the tree section, right? So consider there is a tree given to you. Right? If you do the BFS, breadth first search, if you do the BFS of this, what you will get? You will check each and every breadth, A, then B, then C, and then the next one, that is this. Now, if you check about the DFS, so DFS, you have already know that multiple techniques, pre-order, in order, post-order, right? So consider pre-order now. So this is A, then B, and then you move to D, and then you move to C. So this is called the pre-order. So this is the BFS and DFS of the tree. This is pre-order traversal, simple, right? So and then guess what DFS that we have done. But consider if there is an cycle here, okay? If there is a cycle here, A, B, C, D, and there is a cycle. Now there is a cycle, so you start from A, will go to B, B will again go to C, and the C will again go to A, and A will again go to B. So there's a cycle, right? So we have a infinite loop which we will keep on traversing to traverse the tree. We can keep on repeating the same number of same nodes, right? So this is called the cycle. Okay. So to handle cycles, okay. So the difference between the tree traverse and the graph is only this. We have to handle a cycle in the graph, right? So to handle the cycle, we keep a Boolean array, right, which will keep track whether the node is visited or not visited. Okay, so if we do the BFS here, so in case of a BFS, we basically start with A, right? So we start with A, mark A as visited, right? And as we have a queue system in the BFS, right? So we'll put its adjacent neighbors and queue A, B, C, right? So we'll put B and C in the queue, simple, right? Now we'll pick the next one from the queue and mark it as visited. Okay, this is also visited, right? And this is also visited somewhere in the queue, right? Now we'll pick B from the queue, right? And for B, we'll add all of its adjacent. That is C after this. Now we'll pick C here. Okay. And for C, we'll add all of its adjacent. So adjacents are B and A, both are visited. So we'll not put both A and B, right? And for C, we will pick this now. For D, we will pick this. There is no element which is not visited. So for D, B is visited. So we will ignore D, B. So A, B, C, and D. This is called BFS, that is breadth first search. Okay, let's take an example. Okay, this is the starting node. Tell me the BFS for this. So yeah.